section, we're going to start a new topic called determinants. And let's take a look at some motivating factors for this. So suppose, let's say if you wanted to solve the equation ax equals k, we need to make sure that a does not equal 0. Otherwise, it just wipes out the whole equation. So we see that the leading coefficient can't be 0 in order to solve an equation like this. Now let's move on to a small system. Like so. And if I turn it into an augmented matrix, let me work it until we can determine what it is we need to happen so that there's guaranteed to be solutions. So the first thing I'm going to do is multiply the second row by A. And then I'll try to wipe out that AC that is below the A. So I'll do negative CR1 plus R2. And no, everything's good so far. So let's see what happens then when I do this. I know I get 0 below the A, but what do I get for the other one? I get negative BC plus AD, so I'm going to write it as AD minus BC. And on the other side, we're going to have L minus KC. Now, we know we'll have a solution if this thing right here does not equal 0. Well, we're guaranteed to have a solution no matter what happens on the other side. If this piece right here is not equal to 0, we're guaranteed to have a solution. And this is where we come up with a definition. If you just have a matrix with one item in it, the determinant is, we write it like this, DET A11, that simply equals A11. But if it gets a little more complicated, like the last one, so once again we put the DET in front of the matrix. And this is equal to AD minus BC. So that's what the determinant is for a 2 by 2 matrix. You take the A times D minus BC. So it's sort of like a cross pattern. So we want to extend this idea to larger matrices than just 1 by 1s or 2 by 2s. So here's how we do it for larger matrices. All right, for larger matrices, let's go ahead and write the matrix down. A equals A11, A12, A13, A21, A22, A23, A31, A32, A33. Now we're going to assume that A11 does not equal 0. If it weren't 0, what I would do is simply rotate, swap rows until I got a non-zero item up there. If this whole column was non-zero, then it's a smaller matrix, and I would deal with that a different way. So let's work with that. Now, with that in mind, I'm going to go and try to work this matrix using the row operations as far as I can possibly go. So the first thing I'm going to do is multiply the second and third rows by A11. So I'll do A11 times row 2, A11 times row 3. Now I'm going to start trying to kill, like I normally do, this item and this item. This will get messy, but you'll see we're going somewhere with it. So I will do negative A21 R1 plus R2. And that will wipe out that entry right there. And the other ones will get a little bit more complicated though. So I'll give myself some space. A12, A13. So now I have to do negative A21 times A12 plus this stuff. I'll write it in a slightly different order. I'll go A11, A22 minus A12, A21. And then the same thing goes for the last column. I will have A11, A23 minus A13 times A21. And then I also want to zero out this guy right here. So I will do negative A31 R1 plus R3. So that'll zero that out there. But once again, we'll get ugly terms in here. So I will get A11, A32 minus A12 times A31. And then for this last spot right here, we will get A11, A33 minus A13 times A31. Now this gets cumbersome, so I'm going to make sure that my numbers are easy to see. All right, to guarantee a solution, no matter what column of numbers happens to be on the other side of this thing, we need a pivot in every row. Well, pivot in every row and every column. I've already got my pivot for column 1. For column 2, the only choices we have is this guy here or this guy here. I'm going to assume that this middle term right here is not 0. So we'll make that assumption. Assume basically that it is the pivot right now. What I'm going to do then is multiply the third row by that quantity. So I will take A11, A22 minus A12 times A21, all of that times R3. Of course, my first column, I'll just kind of tuck it in over here. I'm going to need a lot of space, so let me go ahead and start writing my stuff. A11, A22 minus A12, A21 times whatever was there before, A11, A32 minus A12 times A31. The rest of that particular column look like this. And then let me give myself a lot of space over here for the last one. The thing I multiplied by was the A11, A22 minus A12 times A21 times whatever was left in there, A11, A33 minus A13 times A31. And then let me go ahead and put the rest of the column here. All right, now the rest, it's going to get very ugly now, because now I'm going to go through the effort of wiping out this whole quantity right here. So to do that, I will do negative A11, A32 minus A12, A31, all of that times R2, and I will add it to R3. So I'm taking the negative of this thing, so when I attach it to this, I'll have the negative of the whole quantity, and that will zero that part out. However, this quantity down in the last spot will get very ugly looking. So let me go ahead and grab my thing again. It was negative A11, A32 minus A12 times A31, and I am multiplying it to A11, A23 minus A13, A31, and I'm adding it to what was already there, A11, A22 minus A12, A21 times A11, A33 minus A13 times A31. And then let me finish off the rest of this column. And the only thing I really care about now is having a solution no matter what is on the other side of the equal signs for this. That means all of this stuff down here I'm going to want to be the pivot. In other words, I want all of this stuff down here not to equal 0. So this whole chunk right here, we want not to equal 0. That way, if you get a 0 on the other side of the equals or any kind of a number, you'll be able to solve for it no matter what happens over there. So what I'm going to do is multiply that all out. All right, let's go ahead. It's basically foiling is all I'm doing here. I bring my minus over here. I'll start A11, A32 times A11, A23. So I get A11 squared, A32, A23. Then I'll go ahead and take this. With FOIL is FO. So first, then the outer. So A11, A32, A13, A31. And then I'll do the inner. And the inner should get a minus. And then the last. Plus, and I'm going to do the same thing with the other ones, FOIL them all out. So I'll get A11 squared. It looks like A22 times A33. That was the first, of course, of these piece over here. And then I'll do A11, A22 times A13, A31. And then I'll do this piece in here, the inner. And then finally, I will finish it off. All right, and let's see if anything will cancel with each other. So I see I got some A11 squared. That's nice. I know from having done this in the past, I need some terms that do not have an A11 in them. There's one of many mistakes. Let me look at the second pieces then. A11 squared. Yeah, okay. All right, let's see what simplifies now that I fixed it. A12, A12. Once again, I think I found another mistake. So this is a pain in the butt. Let's see, 2-1 there. Huh. All right, assuming that I've corrected everything, let's take those things out and let's see what I get. I get negative A11 squared, A32, A23 minus, well, plus A11, A32, A13 times A31 minus A12, A31, make that a plus, A11, A23, plus A11 squared, A22, A33, minus A11, A22, A13, A31, minus A12, A21, A11, A33. So some of my A's are getting a little cumbersome looking, but let's go ahead. Let me put a line to demark that. Let's go ahead and factor out an A11 from everything. Let's see, I've taken that A11 out of there, so let's... Of course, this is not supposed to equal 0. And that means that I can divide by A11 because I know that it's not 0. So I'm still working with these things here. Now the way I'm going to group them is the following. I'm going to take my A11s together, A11, A22, A33. So anything with an A11, here's that. And I'm going to put it by this one over here, negative A11, A32, A23. And then let me go ahead and do the A12s together. So A12, A31, A23 minus, let me mark these off too as I'm using them so I can keep track of what I'm doing. I'm looking for an A12 down here. There we are. A12, A21, A33. And then I'm looking for A13. What's it attached to? This thing here. A32, A31. And then we are going to match it with this guy down here, minus A13, A22, A31. All right, what I'm going to do then is I'm going to factor out the A11. Then I'm going to factor out the A12. And then I'm going to factor out the A13. And let's make sure it all works out. Let me go back to the matrix itself. What I want to do is, let's start with A1. Let me circle it here. What you do when you go to figure out these things is if I cross out this column and this row, what's left over? We'll take a look at this whole thing here. It'll be the determinant of the things left over, so let me put them in there. Actually, I don't need as much space because these are only 2 by 2, so let's make them smaller. A22, A23, A32, A33. And let's make sure that that piece matches. So I have the A11 now. When we do the determinant, I get A22 times A33 minus A32 times A23, and that's exactly what I have there. Let me move on. For this one, you're going to have to draw the picture again. So let me do my A11, A12, A13. And this time the way you work it is you circle your A12 like I have there. I have it out front. I'm going to cross out its column and its row, and what is left over forms the matrix that I'm going to attach to it. So I have my A21, A23, A31, A33. Now let me make sure that what I have up here matches this. So when I take the determinant, I do A21 times A33. It's close. It's actually the negative of this. And I forgot, there should actually be a negative in front of here. These signs alternate. I should have mentioned that. Let's check to make sure it then works out. I've got negative A21, A33. There's that. Then since we take the negative, but that negative makes it positive, A31, A23. There it is. Plus A13. Let me draw a picture similar to these other ones. Then when I match up the A13, I strike its column and its row, and whatever's left over is what I need to be in this matrix. A21, A22, A31, A32. And let me see if I've got that matched up. So A21, A32, there's that way. And then I have A22, A31, there's that way. Exactly. So that's how we figure out the determinant of a 3 by 3 matrix. We go across this row, what they call expanding across the first row, and we get these things. Now each of these matrices you can take the determinant. Let me do an example. If I try to take the following determinant, I'll do 1, 2, 4, 3, 1, 1, 2, 4, 2. And what I do is I run across the top row. So I start with this 1 times the determinant of a 2 by 2 matrix. And what you do is you strike out its row and its column, and what's left is what you're going to find the determinant of. Now let me take away those if I can. Good. Then you move across the top row to the 2. You alternate the sign though. So when I have the 2, that's the thing I'm looking for. I'll go across and down like so, and whatever's left over will form this determinant, or this matrix here. Alternate the sign again. Let me see if I can get rid of my marks from the last time. Good, got rid of them. Now I'm going to work the 4, mark its column and row, and what do I have left over? DET 3, 1, 2, 4. And then all I need to do is go ahead and compute those determinants. So remember, for a 2 by 2, you do this direction times, so I'll do 1 times 2 minus 4 times 1 minus 2 times 3 times 2 minus 2 times 1. And then finally plus 4 times 3 times 4 minus 2 times 1. And what all do we get? I'll get 2 minus 4, so I'll get negative 2 there. And here I'll get 6 minus 2 times 4. I'll get plus 4 times 12 times 10. So it looks like I get negative 10 plus 40, which is 30. And that's how you do the determinants. You'll be able to see I don't need to extend any longer because this is the general method. You'll see when I do the next one, which is a 4 by 4, it's the same type of a process. So just as a notation, we use absolute value signs around A to denote determinant A. Here then we'll do the determinant of a 4 by 4. I don't know that I mentioned it, but in order to have any mention of a determinant, we need a square matrix. Because remember, when we were designing the determinant, we were trying to ensure that the matrix would be invertible. All right, and then for this, you can just go across the top row. So you'll do 1 times a 3 by 3 determinant. And what do? Take this 1, mark the row and the column off, and what do you have left over? Then you move on along the first row to the next number, which is negative 2. Remember, you do the minus of this one. The signs alternate as you go along. And let me go ahead and take my markings away, if I can. And then we'll take a look at the negative 2. Cross out its column and its row. And what's left over will form our matrix. Once again, alternate signs. So let me go ahead and take my markings away if I can. That spot right there was a 0. It didn't let me take them out all the way. Okay, now I'll go with the 5. Mark its column and its row. And what's left over? 0, 0, 0. 2, negative 4, 5. 2, 0, 5. And then finally alternate the sign again, minus 2 times the determinant. So I will take the 2, mark its column and row, and what's left over? 0, 0, 3, 2, negative 4, negative 3, 2, 0, 3. And then we have to find each and every one of those determinants. That's quite a job in and of itself. Let's start with this first one here. Here I have 0, 3, 0, negative 4, negative 3, 5, 0, 3, 5. So I will go across the first row like before. So I have 0 times the determinant. Well, I did exactly what I said I wouldn't. 0 times what's left over. So if you can start to do this in your head, imagine striking this column and striking this row. What's left? Negative 3, 5, 3, 5. Moving across row 1, now I will go and do -3 because I'm alternating the signs. Now do the same thing in your head. Mark its row and mark its column and see what's left over. -4, 5, 0, 5. And then finally move on to the last 0 and do the same thing. Cross out its row and its column, and we have -4, -3, 0, 3. Now of all these, the zeros don't matter. The only thing that's going to matter here is this particular piece here. So we're going to get -3 times -4 times 5 minus 0 times 5, and that looks like that'll be 60. So this piece right here is 60. Now I'll move on to this one. Here I'll take the double negative out. And let's copy that matrix down. 0, 2, 2. 3, -3, 3. 0, 5, 5. So this will be 2 times a bunch of stuff. Once again, I'll start with this 0, cross out its row and column. And what will that leave? -3, 5, 3, 5. -3, remember you alternate the signs. Do the same thing here and here. I get 2, 2, 5, 5. And then finally moving on to the last 0. Once again, get rid of its row and column. We have 2, -3, 2, 3. Of course, 2 is times all of this thing. The zeros aren't going to amount to much. So we have 2 times -3 times, let's see. Well, this is going to be 0, 2 because you can see that this column and this column are linearly dependent. So in fact, if you take this column and multiply it by 2.5, you get the second column. Well, if they're linearly dependent, then automatically that determinant's equal to 0. So I didn't need to do any of this. All of this is just equal to 0. Next, we'll move on to this one here. Here I have 5 times the determinant. Did I write DET for some of them? I did on some of them. I didn't need them for these because I have the bars. So let me go ahead and put a dot here and a dot here. 0, 0, 0. Now, as I expand along the first row, each of these zeros is going to be a coefficient. I don't need to do any more to tell you that that part's going to be equal to 0. And now we'll move on to the last one. What do we have for that? 0, 0, 3. 2, -4, -3. And 2, 0, 3. Once again, as I start and run my options here, I have a 0 for the first piece and a 0 for the second piece. So I'm just going to have a 3 times a determinant. And cross out, and it's positive 3, in fact. This is -2 times, it's positive 3 because when you alternate signs, you get a plus for the first, but a minus for the second, and then a plus for the third. Get rid of its column and its row, and we get 2, -4, 2, 0. This is negative 6 times 2 times 0 plus 2 times 4. I make a plus because this way is minus, but the negative from the 4 will cancel that. And it looks like 6 times 8, that's negative 48. So what all did we get then? We have a 60 plus 0 minus 48. So this answer then is 12. All right. For A equal, let's just set it to A11, AN1, A1N, ANN. So when dealing with a matrix of this size, we need to define something. Define A sub ij. This is the matrix obtained from A by deleting row I and column J. So the Aij, remember when I was striking out the column and the row that a certain item was in, that's exactly what's going on here. So then we can get the determinant of A to look like this. A will equal A11 times the determinant of A11, where we strike the first column and the first row, minus, remember these alternate, A12 times capital A12. Here, that is the matrix there where I take out the first row and the second column, plus A13. Well, I think you're getting the idea here. And it goes on and on. We'll say plus dot 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 plus. To keep track of the minuses, we have this. Minus 1 to the I plus j. The reason what we do here is, if you look, when I and j are both 1s, this will be negative 1 squared, and so we'll have a positive number. But when I plus j is an odd number, like this one here, we'll get a negative 1. So this will be responsible for alternating the signs. And so there we go. We define the ij cofactor as Cij equals negative 1 to the I plus j times the determinant of Aij. So that takes care of the sign and everything like that. So an easier looking version of the determinant is this: A11 C11 plus A12 C12. That's because we don't have a negative to worry about there, because the C is taking care of whatever sign we need. By doing this, this is called the cofactor expansion along row 1. We can, in fact, do it for any particular row if we want to. Let me show you how this works. The determinant of a matrix I can write like this: AI1 CI1 plus AI2 CI2 plus dot 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 plus AIN CIN. So what you're doing here is you're going across row I. So this says that I can actually do the expansion across any row. So let's redo the last example. Now I'm not going to prove this because the proof is very lengthy and I'm not sure that it does any good. So let's do an example of what I'm talking about, going across any row. Now as I'm scanning this, I noticed that row 2 has a lot of zeros. And whenever you have those zeros, that part of the determinant is going to just wipe out. So I'm going to work down here. And that way, when I do, if I work along this row, this will be my guy right here. When you look at this 0 here, you cross out its row and its column and what's left. So you have 0 times the determinant that's left over, negative 2, 5, 2, negative 4, negative 3, 5, 0, 3, 5. Now we have to make sure it's positive or negative. The coordinate here is the 2, 1 coordinate. So if you take the negative 1 and you take it to the 2 plus 1, that's a negative number. So I should have had a negative in front of the 0, and that's okay, that's what starts me off. Then I know I get a plus in front of the next 0. Not that these matter, but I want you to see the alternating signs. Let me get rid of the things I drew for the last one, see if I can get them. All right, next we're staying along row 2 here. Now I got the next 0. What's left over? 1, 5, 2, 2, negative 3, 5, 2, 3, 5. Get rid of those. And now I'll work the 3. Don't forget to alternate your signs. 1, negative 2, 2. 2, negative 4, 5. 2, 0, 5. And finally plus 0 times whatever is left. So 0 will wipe out this row and this column. We have 1, negative 2, 5. Then we have 2, negative 4, negative 3. And then we have 2, 0, 3. Of course, in practice, I wouldn't bother doing all of this. The only thing that I would bother computing is this guy down here. Because all the rest of these are 0. So all I got to do is work this guy down here. And for this expansion, as you might have guessed, I'm going to go along the last row. So I've got to keep track of my plus and minuses. We always start at plus when we have the 1, but we alternate as we go to the right or down. When we go over one spot, it alternates signs. So this will be a positive. The 1 will be a positive, but the 2 underneath of it will be a negative, but the next 2 will be positive. So I have a positive 2 times what? Well, let me go ahead and cross these out. I get negative 2, 2, negative 4, 5. And then we move on to the next piece, minus 0 times. I really don't care. If I cross out that row and column, it doesn't matter what's left over because 0 times that will make it equal to 0. So I'm not going to bother with even writing anything there. So let's put a star in there. And then we have a plus 5 times, let's go ahead and cross this and this. We have 1, negative 2, 2, negative 4. All right, let's see what we get with all of this then. Negative 3 times, here I'll get 2 times negative 2 times 5 plus 4 times 2. And I'll get plus 5 times 1 times negative 4 minus 2 times negative 2. Let's see what all happens here. It's negative 3 times, here I'm going to get negative 10 plus 8 will be negative 2, times 2 will be negative 4. This piece here is 0, and that ends up being 12, which was a lot faster than the previous attempt at it, because, well, you could have done it way faster than I did it, by just ignoring all these 0 terms and just honing in on just the 1 3 term is all you really would have had to work. Another theorem, the determinant of A also equals A1J C1J plus A2J C2J plus dot 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 plus A1 NJ CNJ. So we can go across columns. As a quick example, like this, I would choose to expand along this column here. Remember, the 4 starts as negative, so we'd have negative 4 times what's left over, 2, 6, 3, 7. And the zeros just zero out whatever determinants I would have in place of them. Negative 4 times 2 times 7 minus 3 times 6. Negative 4. Let's see, we'd have 14 minus 18 is also negative 4. So you can see if you got some zeros in there, you can make quick work of these matrices and their determinants. So for triangular matrices, we have entries below or above the main diagonal are 0. So the situations that can occur, we can have something like this. I guess we'll have like blocks, and then you'll have a block, and this will go down the main diagonal, will be these blocks, and you'll have, say, some stuff up here, I don't know what it is, but you'll have 0 under here. So this would be referred to as a lower triangular matrix. Or we could have what would be known as an upper triangular. Here we would have stuff down below there, but then we would have a 0 up there. I think about it, I may have upper and lower backwards, but it really doesn't matter. The determinant of these things is very simple. The determinant of a triangular matrix is the product of the entries on the main diagonal. So for the proof, I think we'll work a matrix that happens to have the non-zero stuff below the main diagonal. Suppose we have something like this. And each of these, that's like the A11, A22, ANN positions. And we'll pick, we have a star below and a 0 above. It really doesn't matter. We know that Aij equals 0 when I is greater than j. That's where we get the 0 up top there. Now, when we go to find this, the determinant of it, what we're going to do is we can expand along the first row. So I'll get the A11 times a submatrix. So if I take out its column and its row, then what's going to be left? I'll have my A22, A33, ANN, but I'll still have a 0 up here and whatever down there. And I only had to do one entry because the rest were zeros after that. Now moving on, I'm going to expand along the first row again, and I'll get A11 times, this time I'll have A22, which is positive because -1 to the 2 plus 2 is positive 1. So I'll get A22 times a new matrix. Well, the determinant of a new matrix. Here it will be A33, A44, dot, 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 ANN. 0 up here, star down there. And that will be A11, A22, A33, ANN. Now, if we keep doing these along the first row, I'll keep collecting numbers like this. So this will keep going on, A11, A22, dot, 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 until I get to the very end, ANN, and that completes the proof. As a quick example, we have 1, 0, 0, 4, 2, 0, 5, 6, 3. Just multiply the diagonal elements and you'll end up with 6. I should mention that the same exact work that I did for the proof of this theorem will work if the matrix has its zeros below and the star above. It's exactly the same steps.